Hello everyone, I'm Maarten Wijnands from Maastricht University and I will be presenting our IC3D paper which is titled Adaptive Streaming and Rendering of Static Light Fields in the Web Browser. This paper has been realized as a joint effort with my colleagues Hendrik Lievens, Jeroen Put and Nick Michiels, and with Hasselt University student Brent Somers, who actually carried out the bulk of the implementation work. Our supervisors are Professors Peter Kwaks and Wim Lammert. A light field can conceptually perhaps best be explained by comparing it to traditional 2D images. Whereas a 2D image captures only the intensity of the light rays that pass through a physical scene, a light field also captures the direction in which those light rays travel. A static light field does so at a particular moment in time, giving rise to a static, inanimate virtual scene with parallax effect. As such, light field technology is a scanning-based alternative to laborious manual modeling by allowing for high fidelity and ISO-compliant content acquisition directly from the real world. In this talk, I will present the design, implementation, and performance evaluation of a web-based static light field consumption system. The proposed system includes both a network streaming component to dynamically deliver the light field data over a transportation network and a real-time rendering component to visually present the static light field to the user. Our work is a first to bring static light field consumption to web browser contexts. Static light fields are typically captured as a collection of 2D images that are often called source views, which each source view covering the physical object or scene from a different vantage point. In the image on this slide, each gray dot represents a source view. The source view with a magenta border is currently being displayed, while a number of horizontally and vertically adjacent source views are shown in the boxes with blue and red border respectively. As you can imagine, storing each source view as separate images quickly leads to enormous dataset sizes. Therefore, we exploit the widely adopted non-multiview H.264 AVC video codec for static light field compression purposes. This approach has the advantage that it can exploit software and hardware that is commonly available in consumer devices, for example, in the form of dedicated video decoding chipsets on GPUs. In our approach, the composing source view images of a light field dataset are spatially subdivided into rectangular patches and then video encoded in multiple qualities, as you can see in this video here, where each gray dot represents a source view. This way of working enables adaptive network streaming by mapping each spatial patch to a multi-quality MPEG-media segment, which holds a predefined number of spatially adjacent source views, as you can see in this video. The resulting light field dataset is stored on a plain HTTP server and is transferred to the web browser via MPEG-adaptive streaming. For those of you who are not familiar with MPEG-, it is a standardized HTTP adaptive streaming implementation, which in recent years has become the de facto approach to deliver audiovisual content over the internet and is used by popular video platforms like Netflix and YouTube. Web browser client first of all holds a so-called adaptive bitrate controller, which can decide at runtime in which quality to fetch individual MPEG- dataset segments, hereby, for example, accounting for prevailing network conditions. Fetched video segments are stored in encoded form in IndexedDB, which offers NoSQL-like persistent data storage in web browser execution environments. When they become needed for rendering purposes, encoded segments are retrieved from IndexedDB and then decoded using a combination of mp4box.js and the experimental web codecs API. mp4box.js is used to iterate through the encoded source views that are packaged in a single MPEG- segment, while the actual decoding of these individual source views then happens via the web codecs API. This latter API is instrumental to our approach. Without it, precise hardware-accelerated access to individual video frames is not feasible in a web browser context. The resulting decoded source views are stored in memory to allow for fast access. And finally, a decoded source view needs to be converted to WebGL texture before it can be visualized by projecting it on a plane that faces the virtual camera controlled by the consuming user. We conducted an objective evaluation of the client-side video decoding and light field rendering performance of our web-based implementation. Even though our implementation fully supports ABR strategies, this aspect was excluded from our tests. All MPEG- segments that were needed to perform the tests were ex ante downloaded and locally stored in web browser's cache in the form of video encoded blobs. As experiment apparatus, we use a desktop computer equipped with an Intel i9 9900K CPU, an NVIDIA RTX 3080 GPU, 32 gigabytes of DDR4 system memory, and an NVMe SSD. The desktop system ran Windows 10, and we used Google Chrome version 93 as web browser client. The first part of our performance evaluation is a breakdown of the decoding and rendering overhead of our proof of concept implementation. For this, we used a fire truck dataset. This dataset depicts a toy fire truck and some other playful artifacts, as you can see in the 3 sample source views on the top of this slide. The graphics below illustrates the source view layout. Here you can see that this fire truck dataset consists of 15 concentric rings, each containing 120 views for a total of 1,800 views. The dataset is encoded in H.264, both in a 4K spatial resolution at a bitrate of 24 megabits per second, and in a full HD resolution at a bitrate of 12 megabits per second. The source view collection is spatially split into MPEG- segments, where the first frame in each segment is video encoded as an iframe, and the 29 subsequent frames are p-frames. For this experiment, we used rectangular packaging of source views, where each MPEG- segment contains 30 source views using 6x5 spatial patches. In our experiment, we let the virtual camera follow a predefined path horizontally around the light field, triggering numerous MPEG- segment decodes in the process. The table at the top of this slide shows the average processing times for a single segment. And processing in this case includes the video decoding and other rendering-related operations. Keeping in mind that each segment contains 30 light field source views in this experiment, we get average frame times of 3.6 milliseconds for the Full HD variant of the dataset and 8.9 milliseconds for the 4K version of the dataset. Remember that in our implementation, decoded video frames need to be transformed to a WebGL texture for visualization. Currently, there unfortunately exists no way for decoded video frames to stay in GPU memory, which means that decoded frames need to be transferred back to the web browser, where it is converted to a bitmap, which is then again uploaded to the GPU in a WebGL context to be rendered. The creation of the bitmap and the associated necessary memory transfers impose a significant overhead, as you can see in the final 2 columns of the table. In particular, you see an overhead of nearly 11% for the Full HD version of the dataset, and the 4K dataset has a smaller overhead of approximately 6.5%. This indicates that the time to create bigger bitmaps rises less rapidly compared to the time it takes to decode bigger light field source views. In the second part of our performance evaluation, we wanted to investigate whether the way light field datasets are structured into MPEG- segments has a significant impact on rendering performance. Therefore, we packaged the fire truck dataset from the previous experiment in 3 different ways, as shown on this slide. In the second experiment, the virtual camera followed a predetermined path, as shown on the left. The virtual camera first moved sideways, followed by upwards motion, simulating the user's interest to look at the object from above. Then, the camera moved sideways again and ended the path by moving down to the vertical center to conclude the experience. The graphs on the right-hand side of the slide show the average frame times for the 3 packaging strategies. The graphs also include a red line at the 11.11 milliseconds mark, representing the 90 Hz threshold, which is a typical rendering target for VR consumption. In all 3 graphs, we see that there is a significant spike at the start of the experiment, which can be attributed to the fact that the application is still starting up and is performing some bookkeeping and caching operations. Then, looking first at the 3x10 source view packaging mode, the startup period is followed by a period of jittery behavior. This is due to the comparatively small width of this packaging strategy, in conjunction with the horizontal movement at the beginning of the virtual camera path, which causes numerous segment decodes to be triggered. When the first vertical part of the camera path is reached, around frame 500, the frame times stabilize due to the fact that the entire upwards motion is contained in a single segment, thus eliminating decodes along the way. This pattern is then repeated for the final horizontal and vertical part of the camera path, which respectively result in jittery and stable frame times. In contrast to the 3x10 packaging strategy, the 10x3 packaging strategy favors horizontal over vertical continuity. This results in stable behavior at the beginning of the experiment, where the camera performed horizontal movement. The peaking behavior around frame 220 is caused by the camera crossing a horizontal segment boundary. The initial upwards motion causes a drop in rendering performance because of the severe lack of vertical viewpoints present in segments with a 10x3 source view layout. This pattern is then repeated for the final horizontal and vertical part of the camera pod, which respectively result in stable and jittery frame times. The third and final 6x5 packaging strategy contains a rather balanced amount of horizontal and vertical viewpoints. As such, less distinct periods of jittery performance behavior are apparent, although performance drops are still visible because decoding operations remain required when crossing horizontal or vertical segment boundaries. The main benefit of this strategy is that performance stuttering, if it appears, is better spread out or spread out more uniformly. The third and final part of our evaluation assessed the performance impact of applying alpha masking to a static light field dataset. Alpha masking allows irrelevant pixels in source view images to be cropped away by performing a blending operation in a pixel shader. The end result is thus a light field that only shows the object of interest and none of the background that might be captured in the source view images. In our proof of concept light field renderer, alpha masks are implemented as a separate video stream that holds a masking image for each corresponding source view. This implies that alpha masking involves an additional video decoding step next to the alpha blending operation itself. Interestingly, it turns out this has little impact on rendering performance, as can be seen in this table, which shows the average frames per second that was achieved when a virtual camera followed a predefined path consisting of 1000 frames, without and with masking. A possible explanation is that the segments containing the masks are rather efficient to decode, as most frames only contain black and white pixels, resulting in a low bitrate. However, remember from our first experiment that video decoding is only one part of the performance puzzle, in that decoded video frames need to be converted into bitmaps for WebGL texturing purposes. This implies that when applying alpha masking, a bitmap is needed for both the light field source view and its associated alpha mask image, thus effectively doubling the required number of bitmap operations. Surprisingly, the cost of the additional mask bitmapping seems fairly small. So this brings us to our conclusions. In this talk, I have presented our proof of concept realization of a static light field streaming and rendering client that runs in web browser environments. I have discussed the JavaScript implementation of our approach, which leverages technologies and frameworks like MPEG-, the Web Codecs API, and IndexedDB. The JavaScript source code is publicly available in GitHub. Then I've presented a three-stage performance evaluation. Here, I first looked at video decoding versus WebGL rendering overhead, which revealed that a considerable amount of time is spent on copying decoded video decoded video frames between the GPU and the web browser, who transforms source views into WebGL textures in the form of bitmaps. Secondly, I've talked about the performance impact of different strategies for spatially packaging source views into MPEG- segments. Here, it turns out that a square-like packaging strategy is a good heuristic to yield uniform rendering performance. Thirdly, and finally, we found that the performance impact of applying background masking is surprisingly small, given that background masking requires twice the amount of video frames to be decoded compared to a non-masked dataset. In all, it is important to stress that we have invested modest time in optimizing our client-side implementation, which implies that the presented results represent the worst-case scenario and that it thus should be feasible to further improve performance. With this, I would like to thank you for your attention and would like to open up the floor for questions. Thank you.